Good morning. Welcome and a new week, new session. Thank you for joining me this morning. Good attention, good attention. Okay, let's start. I can see some question on the chat box, but I don't know if I really understand this because section 11.1, 11.2 are not even, I think we're not even covering in this course. We will talk about 11.3, I believe. Yes, 11.3. That means no. For exam 2. Yeah, 11.3. Oh no, this will be not 11.1. We're not covering. We used to, but we will not. But the last week of class of the course, we will talk about 11.3, the polar coordinates. Okay, but not, yes, not now. Okay. Let's, yeah, if you have some other questions, you can, yes, Kiran, you can maybe, yeah, you can email me and then I can, yeah, because I've got some question which is sent directly. Don't send direct questions to me now because then it's confusing. I can't address it. And then, yes, yeah, let's start. If you have some questions that you don't want to ask on this chat, you may ask in different way. Okay, that's mean for the exam 2, yes, definitely for the exam 2 is just chapter 10. 10.1 sequences and 10.2 up to 10.5 only, all of the tests. Yes, all of the tests. I think I have the list. I hope you found all of the summary of all of the tests. And now what we will do today, I hope you watch the short session about the root and the ratio test. That's the last test that we will cover. That means I did provide them. I didn't prove. I just provide the test and I apply the test for a couple of examples. But today we will take lots of formulas and lots of infinite series, and we will try to determine convergence or divergence. That's we will try to go through all of the tests, okay? All of the tests that we learn. And this is this session, and the same like last week's session, like last week Tuesday session, can be definitely treated as a review session, yeah, for the exam, because all of the sessions in chapter 10, but definitely last week my Tuesday session and this week Tuesday session is also, I would say, is the good exam review. Okay, that's me. Now let's see what I have. I believe I did this one again, yes, but let me just check. I'm sorry, I think I have it because I want you. Okay, I just printed on different paper, but that's what I'm talking about. Yes, the summary, because this is, I just cut it, but this is the summary and this one. That means it's just basically one page, both sides, talking about all of the tests. It's really helpful. You can find in section 10.5, near the summary, the strategy. Okay, that's mean one more time. Test for divergence, we always have to check this. Geometric one. P-series test, we know that is based on the integral test. We also know the integral. And then we have the tests that we can only use if the terms are positive, comparison, limit comparison, and actually integral. Yes, integral is also for the positive terms. And the negative, alternating series, and the ratio and the root test. That means really quickly, if you still didn't watch, I can just tell, yeah, the test. What we have to do, we have to compute the limit at infinity of that ratio, a sub n plus 1 over a sub n. And if the limit is a finite number smaller than 1, the infinite series will be absolutely convergent. If it's greater than 1 or infinity, diverges. However, if that limit equals to 1, the test doesn't work. We cannot make any conclusion, it's inconclusive. And especially when the formula is just like a ratio of two polynomials, the ratio of two the same function, when we create that ratio, we will always get 1, because we don't change by creating the next term. We're not changing the degree, we're not changing the coefficient. It will be exactly the same, it will be 1. Yeah? But you will learn based on the practice. And then root test, it's similar conclusion, but we're computing a little bit different limit. We're computing the nth root of the absolute value of the terms. And the same actually thing, if that limit is less than 1, absolute convergence, which absolute convergence implies convergence. Yeah, it's also quite powerful tool. Greater than 1 or infinity, the series diverges, and if the limit is 1, is inconclusive. Yeah? And when we can apply the ratio test, if we see the formula that is a little bit like, let's say, way complicated, maybe for the comparison, maybe not even good for the integration, because we will not know what to do, because the formula contains like couple of different expression, exponential, power, maybe factorial, then I will always try the ratio test, especially if we see factorial. The ratio test is quite nice. Lots of terms cancel out because of that ratio, and we can get the conclusion quite fast. Unless it's 1, then we have to find different tests. Root test, I just type something like this. It is really helpful if you have the entire formula taken to the power of n, because applying the nth root, we cancel out this and we can just get the limit easily. Yeah? Hopefully it's not 1. Okay, let's see. And this is also the second page, the second page. Integral test, we actually didn't cover telescoping series. That's we did remove, we used to, but we did remove this. And the strategy for absolute conditional, I just type a couple of steps. You may always take different steps. You may try right away, depends of your way of like thinking. Yes, I can't really check this, but this is just the suggestion, especially these steps, because when we are asked to determine absolute convergence, you may start with absolute value right away and then test the formula, or you may take the original formula and test and then absolute value. Depends which one you prefer. Both ways will be good. Sometimes one way it's faster than another one, but that's not really the case. You will definitely have time. Okay, that's me. Let's start. We remember this session is a good exam review session. Okay. Exercise number 1. Which of the following series converges? 1, 2, and 3. Really quick. Let's go really quick. Okay, because this question you're supposed to answer in less than a minute. Okay, the first one, summation of 1/7/n. It is convergent or divergent? Of course. Yes, I'm waiting for my student. It's a harmonic. It's like a constant multiple of harmonic. This diverges. Harmonic series. Okay, what about the second one? Converges or diverges? The second one is convergent. Oh, I'm sorry, it's also divergent. Diverges by what test? Test for divergence, or the nth term divergence test. But if you use this notation, it's nice. Then I know that you follow my live sessions. Okay, because what we can do for part, we can find a limit. I think I was thinking about, we can find a limit Okay, and we know that this limit is 1/2, natural log of 1/2, limit different than 0. If the limit is different than 0 of the terms, no chance for convergence. Because we remember this, is supposed to, if I will like list the first term, the second term, the third term, I'm adding, and then at the end, the terms are almost like this number, yes, because they approach, the sequence is convergent. That's mean adding natural log of 1/2, natural log of 1/2, and 1/2, we accumulate big number. The series diverges. That means please do not confuse, yeah, because it's easy to think, oh, the sequence converges, but not the series. Okay, and what about the last one? Inverse tangent, how inverse tangent behaves, arctangent, it's also divergent. Because how the terms behaves, we will have the first term, the second term, like inverse tangent of 1, inverse tangent of 2, inverse tangent of 3, and then eventually how inverse tangent behaves at infinity. Please tell me, I can say arctangent. Somebody, I'm looking. Yes, thank you for the help. This is arctangent. It's approaching pi over 2. That's mean we will be keep adding pi over 2, pi over 2, pi over 2. It's divergent. No chance for convergence by the test for divergence and term divergence test. Okay, none of them converge. Okay, good. Exercise number 2. Determine whether this series converge or diverge. If it is converges, find the sum. If we're asking for the sum, what kind of the formula we most likely see? What kind? Geometric. Yes, the geometric, yes, because we know the formula, we know the if it is convergent, we know the formula of the sum, and it's helpful. Okay, that means this is definitely the geometric one, because we know how to recognize when we're looking at the formula, like no addition, no subtraction, unless we can split, and we will have addition or subtraction of 2 geometric. But this one, we have no addition, no subtraction, and n is placed in the exponent only, because it's the exponential form. That's the case, that's the geometric. Now we have to identify the common ratio. The common ratio is the number taken to the power of n only. That means it's -4/5. Yes, thank you, Deepan. -4/5, yes, it's definitely a number between -1 and 1, because that's the condition. If you look at my beautiful summary, okay, it is convergent. Then we may use the sum. If it's not convergent, we're not using this formula, even if we arithmetically can compute this. Okay, 1 minus -4/5, but what is the first term? Yes, we remember what we can do, the first term, yes, it will be, I don't want to put 1a. A is the first term in this formula. We have to just copy exactly what we had. Let me just, and now instead of n, we will put that index. If this initial starting index is 2, 3, 4, or 0, we will substitute that number, because I don't want to say a sub 1 means that n is 1. In this case, it will be n, it is 1, but not always, yes, not always. Okay, that's mean what we have, 0, 3/5. Oh, it is negative. Let's check. No, I think it's positive, right? Positive. Rishabh, please confirm that it's positive. Unless I'm doing something. No, it is 0, 3/5. Okay. Okay. And then 3/5 over adding, we will be adding 9/5. 1/3, because this will be 3/9, 1/3. Okay. Yeah, that's been when we asking for the sum, it's the geometric one. Good. Exercise number 3. Oh, interesting question. Which one of the following statement is true? That means only one is correct. Okay, we may start eliminating the wrong statements. Which one is definitely wrong? Couple of them, actually 4 of them. D. Okay, I like this one because if the limit is 0, we know nothing. Yes, maybe this infinite series is convergent, but not with that reasoning. Correct, not with that reasoning. If the limit is 0, we know nothing. Yeah? Yes, yeah, I'm just thinking. Okay. Also B is also wrong if we have the experience with ratio tests. That means let's maybe really quickly, this will be short, but we can see this is just the polynomials, right? Just one kind of the function. Ratio test is telling us that we have to compute a sub n plus 1 over a sub n. And a sub n plus 1 is n plus 1 to the power of 4, and this is n to the power of 4. I don't have to keep absolute value because it's all of the terms are positive. So let's flip this. This will be 1, n plus 1 to the power of 4, dividing by fraction means multiplying by the reciprocal. N to the power of 4, n to the power of 4, the same coefficient leading, it is 1. Ratio test is inconclusive. And the same will be the root test. We will also get 1. We will get 1. We will get 1, but we have to go, because it will be indeterminate form. Oh no, it will be actually 1. Number to the power of 0, because the nth root, it's in the power form is 1 over n. 1 over n is 0. Any number to the power of 0 is 1 in this case, because n is an integer. Okay, that means it will be definitely that limit. I can maybe post just the limit for the limit of the nth root. Yes, we will get 1. You can check this. If you have to go through the longer way, you can go, but it is 1 because nth root means 1 over n, 1 over big number, small 0. Okay, that means that's wrong. And this is not divergent. We know right away, 1 over n to the power of 4. Okay, that means integral test, or if we would like to narrow a little bit, what test you will actually list if this will be open-ended question? 1 over n to the power of 4 converges, yes, because of the P series test. But we know this is just the shorter version. It's still based on the integral. It's still, yes, but good. I also have this. Okay, good. Now let's look at my exercise number 4. Which of the following statement is false? Okay, that means only one is incorrect, and that will be our answer. Yeah, a little bit of, yeah. And 4 of them are correct. Okay. Okay, that means which one is false, Rachel? I think yes. Is this P series? It's not, yes. N to the power of 5, yes, that's it, but not this one. What formula is this? What type? It's the geometric one, of course. It's the geometric series common ratio is 1/5. Okay, and then it will work, this will work, everything will work, but we're looking for the false answer. Yeah, everything will work. That means this will be the correct answer. Yeah, please also think what we're looking for. Okay. And you may check the ratio, the root test, the integral test, nice integral. And of course, the geometric one, we know almost right away what is the sum. Okay, exercise number 5. Oh, longer. Let's try. Okay, we have A and B, 2 formulas. Which one is convergent? Which one is conditionally convergent? Which one is absolutely convergent, divergent? Okay. What test we will use for the formula A? -1 to the n, and then quantity. It's good for the root test because let's notice we have n and n. We almost have the formula taken to the power, entire formula taken to the power of n. So let's see. Let me just do this. N squared plus 2n plus 1 squared, and then n cubed plus 1. I have to be just careful. Everything is taken to the power of n. Do you think I can write this way? I just pull out that common n. Now, when I take the nth root, that means definitely root test. Yeah, please, I mean, when you have the entire formula taken to the power of n, root test is good. Computing a limit at infinity of the nth root of absolute value. It means limit as n goes to the infinity, nth root, absolute value will remove the -1 to the n, will become positive. That's we will only have n squared, 2n plus 1, n cubed plus 1. Oh, okay. And then everything is taken to the power of n. Am I right? I have to be careful with that. Yes. All depend. I know you. let's see. Let's check. Okay, that means nth root and the n power is gone. And what is the limit inside? What is this limit? Less than 1 or greater than 1 or infinity? I mean, finite number greater than 1 or infinity? Limit at infinity. And what is the degree? It is infinity. Yes, thank you. Because it's n squared, n to the power of 4 versus n cubed, infinity. If the answer of this limit is infinity, the series is divergent. And no, yes, root and the ratio test are quite powerful because it's no option for conditional convergence. No, it's just divergent. Okay, because of this by the root test. But we are not asked. Okay, that means it's not this one, it's not both of them. Maybe C, no option, maybe C or maybe D. Okay, that means now B. Since we see lots of factorials, what test we can use? Ratio test will work. Okay, and I think, did I copy? I copy. That means let's use ratio test. Okay, that's when we practice a little bit of ratio and root test. A sub n plus 1 all over a sub n. Excellent. Limit. But please check the video, and please just redo 5 problems. It will give you good, yes. Okay, absolute value is removing -1 to the n. Then I will put n plus 1 factorial squared, and then 2n plus 1 factorial. That's a sub n plus 1. Dividing by a sub n means multiplying by reciprocal. 2n factorial and then n factorial squared. I don't have to keep absolute value because I've already applied, and n is always positive. Let's simplify. That's the best, the best moment. N plus 1 factorial, I can rewrite as n factorial times n plus 1. And it is squared, I will write again. N factorial, n plus 1. Easier for simplification. 2n factorial, I will keep it. Okay, now we remember this, 2n plus 1, we have to distribute this. That means this is basically 2n plus 2 factorial. Yes, yes, and we need to, that means 2n plus 2 is number 2 more than 2n. Then I will say 2n factorial times 2n plus 1 times 2n plus 2. It's like 5 factorial and 7 factorial. Yeah, we taking the greater number and I'm subtracting 2. 5 factorial times 6 times 7. 5 factorial times 6 times 7. Okay, and n factorial squared, n factorial, n factorial. Okay, nice moment. This and this and this is cancelled. 2n factorial, 2n factorial. Okay, and what stays? It is limit less than 1, n plus 1, n plus 1. Always be careful to copy everything. 2n plus 1, 2n plus 2. Okay, what is the limit? N squared versus 4n squared when we distribute everything. Yes, 1/4 less than 1. This series is absolutely convergent, because it's let me say absolutely convergent by a ratio test, because ratio test is testing absolute convergence. Okay, really nice practice. But yes, you have to write down, because when we're writing, it's better connection, body and mind connection with everything. Okay. Okay, absolutely convergent. Nice example. A little bit maybe time consuming, but the rest of the questions you can solve it like just by looking. Okay, good question. Don't miss it. Exercise number 6. Determine whether the series is convergent or divergent. Oh, interesting formula. -1 to the n minus 1 sine of pi over 2n. What test we can use? This is just convergent or divergent. Yes, since we see -1, we can use alternating series test. That's what we have to know. First of all, we have to identify B sub n. B sub n is the part of the formula without the alternation, because that's important. Okay, that's it. And now we remember the condition. It's quite easy test if it works. B sub n must be positive, limit at infinity must be 0, and must be decreasing. If B sub n satisfies all of these 3 conditions, and it, of course, for the alternating one, then the series is convergent by AST. Okay, let's check. B sub n, I can copy the formula for my students. Do you think it's positive? I was gonna ask you. Do you think sine over pi over 2n, it's positive? Always? When n is, let me check, greater than 0, still question mark. For n, yeah, I mean for n greater than 1, yes, starting from 1. How can we, it is, yes. What we can do, maybe, I don't know if this is good, if this is n, this is B sub n, because this is sine function. Yes, sine function looks like this. If n is 1, what is the term if n is 1? How can I say? Okay, B sub 1 is sine of pi over 2. What is B sub 2? Sine of pi over 4. B sub 3, it's just even numbers, times 2 times, yes, 2 times n, of pi over 6, and then sine of pi over 8. That's 4, and so on. Yeah, that's me. Let's start. This is pi over 2. This is the value 1. Yes, because this is sine. Okay, let's say, yeah, it is convergent. Okay, yeah, I can see my students are working. I just want to check that we can see it's definitely positive because pi over 2 and then pi over 4 and then actually half, yes? Pi over 6, pi over 8. If the denominator is increasing, the whole fraction is smaller, that means we're going pi over 8, pi over 10, pi over like 12, and so on and so on. That means the values are, yes, definitely positive. That means no question mark, definitely. What about limit? How we can compute this limit? How this expression, sine of pi over 2n, behaves at any, if n is infinity. Pi over big number is 0. Sine at 0, it is 0. All right? That's we satisfying this, we satisfying this. What about decreasing? Can we say that this is decreasing at the values? Decreasing, because we can see 1, the value is 1, and then it's smaller, 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 smaller. It's definitely. I think if this will be open-ended question, that graph will say everything. We can still try to find the derivative because we remember the strongest tool to prove that the function is decreasing for all of the values like greater than 1. It's find the interval of decrease, first derivative. But this graph is showing us everything. Okay. Not we, B sub n satisfy this, this, and this, we can say this infinite series is convergent. Nice example by AST. Okay, convergent by AST. Because of that -1, we were able to do this. Okay. That means it is convergent by AST. Now let's look at my exercise number 7. Determine whether the series is absolutely convergent. Do you think it's absolutely convergent? What we have to do, it's no, we will see. I will copy this. Oh, actually, it's supposed to be the same, -1. Yeah, I didn't type this -1. Okay. Sine of pi over 2. And actually, let me put this. I can't write so high. Or maybe I can. -1, just in case if somebody will. Okay, now we're taking absolute value because we're trying to check the absolute value. -1 to the n will be gone, and absolute value of that, actually the terms are positive. That means we can just keep it this way. Okay, so now we have sine of pi over 2n, just this. And now the question is this series convergent? Because if it is convergent, then the original one is absolutely convergent. What test we can use? Sine of pi over 2n. It is not, yes, it's definitely divergent, but what test? For this example, we will try to compare because all of the terms are, the terms are positive, and I will try to compare with this one. Yes, oh no, the limit is 0. Here or here, I don't know. The limit is 0, that means test for divergence. Test for divergence is not applicable because the limit is 0. Sine of 0 is 0. If the limit is 0, we know nothing. Okay, please, please make sure that we, okay, test for divergence is not a case. Okay, but I will try to compare with that angle. The problem is, I don't know if I want to really establish the relationship. Can you explain it why? Oh, limit 0. Do you see, we just found the limit for AST. I just explained all of the terms are approaching 0. Yeah? Sine of pi over 2, sine of pi over 4, sine of pi over 6, sine of pi over 8, sine of pi over 10, and I'm gonna go lower and lower. Yeah, it's going this way. Okay, please tell me that you're right, that you're okay. Or you can tell me that you're not okay. Yeah, the limit is 0. Oh, actually, we can just do algebraically, but this is like more, the graph is, yes, what is this limit at infinity? Function is continuous. We're just looking at the limit of the inner function. Pi over big number is 0. Sine at 0 is 0. Yeah? So does it mean that it's converged? No. This is test for divergence. Test for divergence only tests divergence. We cannot say convergent by test for divergence. That's a little bit funny. Yeah, this is the reason. This is the reason that I call test for divergence. Then my students will say, okay, this test only tests divergence. Okay, it's the top test, only test divergence. We can only test divergence. If we cannot, we're looking for different tests. Okay. Also, since we're talking about this, please remember AST, alternating series test. The name doesn't say, but this test, if works, only test convergence. Okay, only works for, only test convergence. Check, check, and check. If the formula B sub n doesn't satisfy one of the conditions, the test is not applicable. We have to find different tests. Please do not say, never ever, that the infinite series is, I don't want to even say, divergent by AST. No. That's not the case. We cannot, that test is not testing divergence. This test is a little bit like not so powerful, because if B sub n doesn't satisfy all of this condition, then the test is not applicable. Please remember, okay? We cannot say, oh, B sub n doesn't satisfy one of the condition, the series is divergent. No. Let's find different tests, okay? The same for the test for divergence, only test divergence. Okay, that's me no, the limit is 0, we know nothing. Okay, let's come back really quickly. We will compare, okay? That's of course a little bit of my suggestion. I will not spend time thinking which expression is greater, which expression is like smaller, because I will need this for the direct comparison test. That means I am skipping direct comparison test, but I will do the limit comparison. Okay, let's see if this works. Limit as n goes to infinity, a sub n over b sub n. A sub n is the original formula, b sub n is the new one that we're comparing with. Limit, okay? And then we can even think about the summation, yes, for the same number of terms. That means I'm comparing with this one. It is absolutely, let's check. Okay, sine of pi over 2n over, okay. What is this limit? Sine over pi over 2n over pi over 2n. If n is infinity, pi over infinity is 0. That's when we do have a case, sine of 0 over 0. And it's identical 0, we can see, identical. Sine of 0 over 0, the identical 0, it is 1. Do you remember? Or if you would like to be more like careful, oh, why is sine of 0 over 1? This is also 0, because this is the same. Yes, this is the same, pi over 2n, pi over 2n. That means in general, I can say is 0 over 0. Yes, it's 0 over 0. Then we may use the L'Hopital rule. Let's do it really quickly. Oh, for the L'Hopital, we remember we have to do the x. Derivative of sine is cosine of pi over 2x times derivative of pi over 2x. Let me write this, times derivative. I didn't compute the derivative. And in the denominator, I also have to find the derivative. Since the derivatives are the same, I can cancel them out. I can even save time. Okay, and then we have pi over big number 0, cosine at 0 is 1. That means you can use the property right away and say 1, or you can use the L'Hopital rule just one step. And if the limit is 1, positive finite number, then now the conclusion. Both of them behaves the same, okay? What is this? Because this was the new one that I'm comparing. Is this infinite series convergent or divergent? Pi over 2n. Because now both of them behaves the same because of that limit being a finite number. Oh, it's harmonic, right? It is harmonic, divergent. Divergent, because pi over 2 is constant, 1 over n. Yes, thank you, Aiden. Divergent, then this one is also divergent. That means this one, oh, how can I say? Let's say this way. Divergent by limit comparison test. And we're comparing with this. Okay, divergent by the limit comparison test. I mean the constant multiple of harmonic. Shall I write? I can put pi over 2 outside, and this will be 1 over n. Of course, it is harmonic. Yes, constant we can pull out outside. That means it's harmonic divergent. Okay, but the original one is not harmonic. It's divergent by comparing with the harmonic through the limit comparison. Okay, through the limit comparison. Okay, that means it's not absolutely. How can I say? Absolute convergence is not a case. And in general, what we can say, it's not absolutely convergent, but do you think it's conditionally convergent? If the question will be determine whether it's absolutely convergent or conditionally convergent or divergent. What we can say? It's not absolutely convergent. Yeah, we did absolute value, didn't work. But I will switch the slide for exercise number 6. We did the original formula and it is convergent. But taking absolute value, it is not. That's mean, yes, it's conditionally. I can add this. Conditionally convergent. Conditionally convergent. Yeah? Because it is convergent, but it's not. Absolute convergence wasn't the case, and we have the work on the next one. Yes, CC. Nice example, really nice, because the test, AST, it's interesting here, and comparison, limit comparison. Okay. Okay, what else? Oh, I have this. Let me check what I have. Oh, okay, perfect. I have exercise number 8, and I have A, B, C, D, E, F, G, H, I, J, K. I don't know how many letters it is. 2, 4, 6, 7, 11. Okay. That's what we can do. We don't have to do everything, maybe a little bit, but I'm really hoping that just by looking, some of you will tell me, or maybe most of you, there will be review, published with the bunch. Oh, it is. I think, Aiden, I've already posted I've already posted the review packet. Yes, on I hope it's visible on Canvas in week 8. Yes. Oh, yes, I did it. Okay. Let's see if we can do like quite quickly, not really putting lots of work, and you can do the work because you know how to do. Okay, first one. We have to determine whether it's AC, CC, or D. Okay, what do you think about the first one? Negative 1 to the n over 1 plus square root of n. It is CC. Because it is convergent, yeah, it is this. Convergent by AST, when we take absolute value, alternating is not a case, and this is telling us n to the power of 1/2. whatever comparison or limit comparison we will do, or maybe even integration. I don't know if we can easily comparison will be good. We will get divergence. That means it is conditionally convergent. Okay, you can maybe rewatch whatever I say, okay, and then you can do the work. Okay, next one. Next one. Yes, thank you. Next one is easy. Next one is definitely divergent. The limit, we can see this limit, it's 1, meaning that it's positive, negative 1, even if we messed up a little bit the limit, but I mean, no. Test for divergence, yeah? Limit different than 0. If the limit is different than 0 of a sub n, no chance for convergence. Which one also is divergent? By test for divergence. E, yes, because this limit is 1. Positive, negative 1 limit does not exist. Test for divergence. And one more on this side. Limit is infinity. Yeah, this one is infinity, but it's plus and minus infinity. Also, the limit does not exist. Test for divergence. And term divergence test, but testing just divergence. Okay, good. Okay, which one? C. What we can say about C? It's absolutely convergent, really good. What I can write, I hope we remember, especially from the first section in chapter 10, sequences, cosine of n pi behaves like negative 1 to the n. Yeah. And this is n to the power of 1, n to the power of half, 3 halves. Okay, that means this formula is definitely convergent by AST. You can check. And if we take absolute value, negative 1 is gone, negative 1 to the n, and we will have 1 over n to the power of 3 halves. P-series test, convergent. What color I can use? Let's say green. Absolutely convergent. Okay, absolutely convergent. Okay, because AST and even removing alternation it is. Okay, what about G? I mean, no, D. Let's go D. Yeah, it's quite maybe big formula, but it's definitely alternating. And if you will carefully check, it will be convergent. It will be convergent because this formula is definitely limit is 0, all of the terms are positive, and it is decreasing. You will check the derivative. You will get. That means this is convergent by AST, taking absolute value, we're removing alternation, and we only looking at this, the main formula, and we only focusing on this if we would like to compare. N squared over versus n cubed will give us 1 over n, harmonic, divergent. Direct comparison or maybe limit comparison. That means not absolutely convergent, convergent by AST. I need blue color. Oh, lighter blue. Conditionally convergent. Thank you. Okay, and the last one on this page. Similar justification. Yes, it will be AC, absolute convergence. Convergent by AST, definitely. Yeah. Positive, limit 0, and you will prove that is decreasing. What color I need? Green. But now, removing negative 1 to the n because of the absolute value, we will focus on the leading terms, and when we cancel out, it's 1 over n squared. We will compare limit or direct to the convergent one. That means it will be convergent. Yeah? You can definitely write down everything. I will recommend. Yeah? Then your test will be like a breeze. But you have to make this connection. Okay, I feel good energy. Because we know the best currency in life that you can give to somebody is your energy. Nothing else matters. You know that. And I can feel energy in this classroom. I can feel it. Okay, and the last four for today. Good review. Okay, good review. Please, yeah, please. Okay. Oh, I don't know if we can do really quickly this one. Or maybe age. Maybe age. What test we will use? We will use the root test because they all alternating. We will use the root test. And what will be the limit when we will take the nth root? This will be gone. This will be gone for the nth root. The limit will be less 2/3. Thank you. Less than 1, absolute convergence. What color? Green. I use green color. And you can try. Okay, you can try by the root test. Okay, what about I? Can we also use the root test? But then what we can, even if we use the root test, what is the limit at infinity? It will be 0, yes, because the root test, let's maybe write this. You can do. We will take the nth root of absolute value because of that cosine. I just want to make sure. Limit. -1 to the n is gone because absolute value will remove to the power of n and nth root. This is gone. Okay, and what is this limit? Cosine of n, 3n plus 2. N, 3n is big, infinity. Cosine of n, only like oscillate between 1 and +1. That's mean 1 maximum value, 1 versus big number, 1 over big number is a small number. Okay, definitely the squeeze theorem is a good theorem to get that limit. Yeah? But limit is 0. If the limit is 0, this is 0 is good. 0 is good, less than 1. Yeah? That means it is absolutely convergent by the root test. Good formula. Okay. What about J? What about J? It is already root test. I mean nth root. That means I don't know if we can use the root test again. Deepen says it's divergent. Rachel is confirming the test. Of course, it is divergent, the test for divergence. If limit, actually, what is the limit at infinity? Since we have -1, we remember we can take absolute value, and if we will take absolute value on, I don't like corrections, -1 to the n is gone. That means this will be just nth root of 3, and this is 3 to the power of 1 over n. 1 over big number is a small number, 0. That means limit is different than 0. And getting back to the original alternating sequence, we will have +1, -1, +1, -1. That means limit of this formula at infinity does not exist as a one finite number. Yeah? That means, yeah, it is definitely test for divergence by test for divergence. Nth term divergence test. I still have to say this for. Okay, and the last one, the last one I will not really guess, even the strong educated guess, but what test we can apply? And let's maybe apply, and this will be our last problem. I can copy this. We can do the ratio test. Let's try. You can do it. Or maybe we did similar. Oh, no, I don't know. It is greater than 1, 5/4. Yes, okay, deepen you too fast. Then it's divergent. right? No chance for conditional convergence, no. I don't have a slide. Therefore, it's divergent. But shall we do? Let's do it. Then everybody will have it. But what you can do, you can definitely try to do on your own. Okay. But let's say this is K. And did I type the formula? Starting with 1, negative 1 to the n, 5 to the n factorial actually squared, and 2n factorial. 2n factorial, yes. 2n factorial is quite fast, but we do have also 5 to the n exponential. Okay, definitely ratio test. I mean, we will finalize the session with this. Let's see if we will get 5 over 4. Deepen. We will check. A sub n plus 1 over a sub n, limit at infinity, and let's check. Negative 1 is gone because absolute value. Now let me expand. 5 to the power of n plus 1 will be this. N plus 1 factorial. That means n plus 1 factorial and another one because it's squared. And then, okay, let me write this way. Okay, 2, because that's all important. Not just plus 1, n plus 1, and we have to distribute 2. And dividing by reciprocal of a sub. I mean, multiplying by the reciprocal. 2n factorial, 5 to the n factorial, n factorial. We don't have to keep absolute value because it's positive. Okay, at least this one. One more step. And we will know the limit. N plus 1 factorial is n factorial times n plus 1. N factorial times n plus 1. 2n factorial. Now we know that this is 2n plus 2 factorial. 2n factorial, 2n plus 1, 2n plus 2, 2. And then n factorial, n factorial. And now these factorials are gone, actually this one. And, yes, I was looking for that 5. I forgot that 5 is so important. Oh, wow. It's so important, yeah, because this coefficient changed everything. Okay. That's always here. It's nice to cancel out, but we have to be really careful because now we have the same degree, n plus 1, n plus 1, 2n plus 1, 2n plus 2. Did I copy everything? I will check because I know that it's easy to miss, but thank you, Deepan. I will check this. Okay, n squared, 5n squared versus 4n squared, 5 over 4. Greater than 1. If I will miss that 5, everything will change. Okay, that means it is divergent. And no, yes, ratio and root test, no chance for like conditional convergence. Okay, that means it is divergent by ratio test. Okay, that's it. Please redo. It will be perfect practice. And in your midterm 2, exam 2 module, you have also practice problems that I prepared for you because I want to keep you busy. Okay, perfect timing. And please, this week and the last week, especially my sessions. And actually, yes, tomorrow, I think you will have a session, live session with Caroline, I think. It will be also the review session. Okay, also the review session. Please practice every day a little bit. I know that I'm repeating myself, and then you will ace it, everything in your life. Okay, thank you, and yes, see you next time. Thank you. Oh, okay, I can stay for some questions. I found negative 12 over 20. Which one? Thank you. I have confusion on what is simplify into, you mean geometric, GP, you mean geometric series, right? Let me come back. You mean the question that we did? Oh, where am I? This one? No. Are you talking about this question? Rishabh? Yes, but where is maybe, if we make some mistake, but you saying -3/4. Oh, you did, okay, I think I know what you did. We don't have to use the algebra so much, because then we can make, you did this, right? 3, and then -4 to the power of n, -4 to the power of -1, and then 5 to the n. That means the formula, let's check. It will be actually, okay, you're right. 3, -4, and then -4. That's your formula? Oh, you're missing -4/5. Do you see? You missing? I'm just looking at your post. Oh, you sent directly to me. You have to send to everybody, because then students in the classroom, they don't see it. You type the formula like this one. Yeah, that's what Rishabh typed to me, but you miss the -4/5. Yeah. And now when you would like to compute the first term, you will substitute that one and you will get 3/5. Make sense? Okay, but send always direct to everybody. Okay, when don't be, yes, you texting, you like posting every day something. Don't be afraid. Everybody has to see this. Okay. Okay. That's, we corrected this one. Okay. That's me. Now I can finish the session. Maybe just one more comment for the discussion. Most of the students contributing perfectly, but please also, like, yes, what I want from the discussion post. I don't want to be just the assignment that, oh, you will just type something and she will grade it. I will get my points. No. Feel the value, contribute as much as possible to the class discussion. Okay, provide something like meaningful, mathematically meaningful. Please, yeah, please do this. And also, you don't have to ask me for the extension if you miss the discussion. One more time, discussions are open for the entire semester until last day of July. If you didn't get the full credit, you don't even have to correct, type something else, type something additional post in that particular week. You can go and review, yes? Also, don't participate in the last minute because you're not giving chance for other students to reply. No? Because this means that you're only looking for the grades, you're not looking, yes, at the deeper meaning of this class. Okay, that means discussions, yeah, make yourself worth, yeah, like show me that you are the, like, show me the quality of you as a student in this class through the discussion assignment. Okay? Don't just type something that I will grade and then you will tell me, oh, I did satisfy everything. You subtract 1 point. Yeah, doesn't matter. I can give everybody the full credit for the discussion. Doesn't matter. Yeah, show me your feel the quality of the work that you're typing. Yeah, not just because you have to do something, because you want to contribute. You want to share some solutions. You want to show your instructor that you know at least one question in this week. Yeah. Make everything nice and beautiful, neat. Okay, I just wanted to say this. But again, most of the students are typing beautiful solutions, and you can share the solutions. Yeah? You don't have to check internet. You don't have to ask behind this. You can ask actually in the classroom. Okay. I will not keep you longer. Thank you. Practice every day, make beautiful discussions, and see you next time. Thank you.